We're given a 100-gram mass at the end of a beam, and the beam's rotating, and the mass is, I believe, 40 centimeters. Yeah, 40 centimeters from the axis of rotation. So the beam is rotating like this, about an axis, and the 100-gram mass is 40 centimeters from that axis. And its rotation of the beam is at 2 revolutions per second. Okay, and there's also an acceleration. Let's just take the 2 revolutions per second, because that's what we need to use to answer the first question. We don't need to worry about the acceleration. Matter of fact, I don't think the acceleration is mentioned in the first question, just the velocity. So we're asked what the kinetic energy of that 100-gram mass is. Okay, well, to get the kinetic energy of a mass that's that's moving at some speed, we have to know how fast it's moving, and we have to know its mass. Well, it's sufficient to know its mass and how fast it's moving. Okay, we know the mass of this object, it's 100 grams. How fast is it moving? You can't say it's moving at 2 radians per second, because we're talking about speed through space, not speed of rotation. If there's a 100-gram mass at the end of this beam, it's moving faster than another 100-gram mass only halfway to the end, because it's got further to move in a revolution. So how do we get how fast it's moving? Well, there are 2 ways to do this, and we really need to understand this not by quoting a formula, not even circumference equals 2 pi r. We want to really try to understand this in terms of 2 simple things. One is the definition of the radian, and the other is the definition of pi. Now, people came up with the definition of pi pretty quickly, but having been nagged for a week to know the definition of a radian, people still don't know it. And that's, I remember, I was there. For some reason, that's hard to remember, but once you got it, once you understand what it means, it's incredibly simple. So you really want to know that definition, and you want to keep using the definition, not formulas that come from the definition. You can get all those formulas if you just know the definition. You don't need the formulas if you just know the definition. Okay, well, from the definition of pi, we can figure out how far this thing travels around the circle in 1 revolution. Now, you would say, well, why don't we just use 2 pi r, because that's the circumference. Well, among other things, people confuse that with pi r squared. I haven't encountered that in the engineering group, and usually don't, but it happens. And that's so wrong on so many levels, but I'm not going to get into that. So, I just don't think people are quite secure enough on the fundamentals to be quoting formulas when there's an alternative. Sometimes there's no alternative. You've got to quote formulas sometimes. Formula for the surface area of a sphere. You're going to get to that very shortly in multivariable calculus, but until you do, you probably don't understand how that area is derived. That's just kind of a formula you got to use when you need it. Or the volume of a sphere, or many other things that you know by formula that you'll soon know by integration. Okay, well, that's a digression. From the definition of pi, we can determine how fast this thing's moving, because the definition of pi is it's a ratio of the circumference to the diameter. Now, if pi is the ratio of circumference to diameter, pi is circumference divided by diameter, so circumference is pi multiplied by diameter, and diameter is twice the radius, so it's 2 pi r, not pi r squared. Okay, again, nobody made that pi r squared error. I don't think I've seen that one this year. I think I saw it last year. At least not among engineering students. Okay, so by the definition of pi, we know that this thing moves 2 pi times 40 centimeters in 1 revolution. Not from the formula 2 pi r, from the definition of pi as a ratio of circumference to diameter. And of course we know that diameter is double the radius. Okay, so the speed is what? Well, it's 2 revolutions per second. We can multiply that by 80 pi centimeters per revolution. and our revolutions divide out. We end up with centimeters per second, so formally that works. And common sense, that works. If we're doing 2 revolutions in a second, and each revolution takes us through 80 pi centimeters of motion along the arc, then certainly at 2 revolutions per second, we're going to travel 160 pi centimeters every second. So there's the speed, and we can put that together with the mass and do 1/2 mv squared, and we get 1.2 joules. So we've got it. We didn't need to know what radians were. We didn't need to know nothing else. Of course, how did we get the fact that, we got the fact. We got the 2 pi just from the definition of pi. Okay, well, the definition of a radian is closely related to the definition of pi. The radian is just, now I didn't draw this in class because I didn't want to take time, because it's taken us a lot of time to get through this, but here's a circle. And there's a reasonably badly positioned set of coordinate axes. And a radian is an angle that's about here. And it has the property that the distance we travel, if we travel this arc, is equal to the radius. So this is almost like an equilateral triangle. If we were to straighten out this arc, well, that would move this out just a little bit. You know, pound that arc into a straight line, that's going to move this out. It's going to move us out to where we have an equilateral triangle, because this distance along the arc, the length of whatever we bent into this shape, is equal to the radius. Okay, so radian is a little less than 60 degrees, just by that. Now you can use your conversion that everybody seems to have memorized, but nobody seems to understand. Conversion between radians and degrees. But you're not converting in terms of the definition of a radian. It's a very short step from the definition of a radian to that conversion. Because, of course, we know that the total distance around this arc is 2 pi times the radius. Now, if each radian has a distance that's equal to the radius, and the circumference has a length that's equal to 2 pi times the radius, that means that you have 2 pi radians around the circle. Make sure you understand that. So, simple definition of a radian, simple definition of pi leads to the solution. And using the definition of a radian, we can simply say that the speed is the 4 pi radians per second. By the 40 centimeters we move along the arc for every radian. The radius being 40 centimeters, we have 40 centimeters along the arc for every radian. So for every radian we move 40 centimeters, we move 4 pi radians every second, so we move 160 pi centimeters every second. So you think of this reasoning, think of what it means to have a couple of simple definitions and for everything else to fall out of that definition, so you don't have to memorize a dozen or 2 formulas, and see if that doesn't help in many, many applications. Okay. Okay, the next question involves the acceleration of the object along the arc, and also there's something related to centripetal acceleration that was asked, but we didn't get to solve it because it took us quite a while to do this. So we'll address that in the next video.